So we are in lecture 4 for the quantum butterfly in the quantum world. And today we're going to mostly talk about properties of quantum mechanics and material science, related a little bit to the butterfly, but mostly provide background material to connect the butterfly to topology in the next talk. So they spent a whole chapter introducing concepts in quantum mechanics, which most of us are a little more familiar with here. But just to briefly summarize, Planck started a lot of things off by recognizing that black body radiation can be quantized into quanta, which was then followed up by Einstein and his realization of the photoelectric effect, which has emission of photonic wave packets. So light has particle properties. And Bohr then realized that these discrete spectral lines can be described, which eventually was found in the theory of quantum mechanics, which was developed later. And part of those developments included de Broglie's notion of a wavelength and frequency associated with quanta of momentum and energy. And then there was Heisenberg's matrix mechanics, which then probably von Neumann realized could be represented in terms of a Hilbert space. And Schrodinger's wave equation was also found to be equivalent to the matrix mechanics, giving us the theory of quantum mechanics. And also, it's important to note that the double slit experiment really showed that both light and matter behave similarly like quanta, neither particle nor waves.
And what's nice about that list is everything except for the double slit experiment is in chronological order, so it's a really concise, kind of simplified history.
Yeah, this kind of came before and after.
Actually, yeah. The double slit experiment came after almost all of that stuff.
I thought it was.
No, it was after. After Heisenberg's and Schrodinger's wave equation, nobody had done the double slit experiment. Nobody had thought of that. And one guy published a paper saying this is an implication of it.
Oh.
And it took a while before they actually tested it. But that came after Heisenberg and Schrodinger.
Because you needed a laser, no?
Young definitely did some experiments in the early 1800s.
Young did, yeah,
with
photon
some
experiments. He
photon
did it with
experiments.
light. But the double, so
But
they had a double
light
slit with
is-
light, yeah, but in those days, I mean, I guess.
The
yeah,
matter came after.
Yeah, double slits with
Certainly
matter,
after.
electrons that can.
Oh,
So-
the double. I'm talking about the double slit where there's a detector and it collapses the pattern on the screen.
Oh, yeah.
That wasn't done until.
So they just had the interference patterns beforehand in the
Yeah,
early
there's patterns
1800s.
from light beforehand.
Yeah.
Which was done probably hundreds of years. You
Yeah.
do that, with a cone.
Like he said, Young did it in the early 1800s.
Okay. Okay.
Yeah,
got it.
yeah.
What is that
So that is
thing you're
chronological then,
animating?
all the way.
This is actually just some wave packet. I believe this one is diffusive, it looks like, but dispersive, I should say, sorry. But it's just a wave packet traveling.
I mean, for predictions of the wave, if you imagine a complex number, and that's the graph of it. I mean,
Yeah, it's spreading out.
It's
That's the
dispersive.
dispersion.
Yeah, it's
Yeah, so that
it's a
could be a
weird one.
one-dimensional quantum wave, and it's showing that the perpendicular plane is the complex plane.
Yeah.
That could be what it's showing.
And you made it with Mathematica?
No, I just found on the internet some GIF. It's just a wave packet.
Yeah.
Awesome. So another important experiment is noticing this Ehrenberg-Sadeh-Aharonov-Bohm effect, because actually these guys discovered it first, but Aharonov and Bohm really popularized it, which is this notion that previously it was thought that electric and magnetic fields were physical. And in this experiment, what they end up doing is they have magnetic flux. So you can have some solenoid with coils wrapping around, and this will create a magnetic field inside the solenoid, but the magnetic field will be zero outside the solenoid. And if you take an electron and you send it around one way versus the other way, if it only depended on the magnetic field at that position, then there should be no electromagnetic effect. But what was found experimentally is that there's actually a phase shift in the wave function, even when the magnetic field is zero on the red lines. So what this means is there's actually something deeper underlying this electromagnetic effect, which is described by this electromagnetic potential A mu, which is often thought of as being the photon or the quantum potential for electromagnetism. So this experiment really for electromagnetism, really put quantum electrodynamics on the map in the sense that we need to talk about a mu quantum mechanically.
Sorry, you said that all perfectly. Would you mind just rephrasing one more time, just so I can get it double?
Yeah, definitely. So in this experiment, we have a magnetic field that is confined to only be inside this cylinder. And so in all of the white regions, especially along the red paths, the magnetic field is 0. But if you send a particle along a closed path that encloses some magnetic flux, then it ends up actually causing a phase shift. And that is described by this potential a mu. And the wave function of the particle, or the quanta that you're transporting. Like, let's say this guy. This is just depicting, like, you could send it to the left or to the right. And the point, you could think of it as one going to the left, one going to the right, or you could think of as just one particle going in a circle and enclosing a loop. But that's the basic point, is that you can think of this being some like non-trivial puncture almost, because this could be confined to a delta function spike, and there would be almost no magnetic field anywhere except right at that point. But if you enclose it, it still has topological, it's a topological notion because it doesn't matter the precise path. I take this red line, this world line could be deformed topologically. As long as it still encloses this puncture, it still is going to have that effect.
So, and only if it's around this solenoid. So it's interesting because the interference of the two probability pathways, right, in the phase shift representation is indicating, you know, a really fundamental topological quantum effect, and it needs the solenoid in order for it to do it. But what's interesting is that it's not in relation to a force around, like a classic electromechanical.
Exactly. It is a subtle effect in the fact that it is this phase shift of the wave function.
Okay.
So
This is classical?
you can actually treat it classically, technically, but it was discovered as a quantum mechanical effect. It's typically called a quantum mechanical
If
effect.
not classical, then that means that the flux can maybe it would cause this effect, even if it's a little bit deviated from the path. Doesn't have to be like right on the path.
Oh, I see.
What do you mean? It has to be
The magnetic flux right now, it's kind of like, you know, if you go straight line, it will be on the path. So
There's a difference of what you get from going left versus going right.
And they interfere
Yeah,
with
the path doesn't go through where the flux is. The path goes around it. The flux is surrounded by some kind of tube that prevents the electron from actually going inside the tube.
but the two paths interfere with each other, which is a quantum.
so I thought the path is supposed to be like this, and then because of the flux there, and then it either goes this way or that way. But what you're saying is
No, this is a
it was
different.
supposed to go this way.
So if we had some magnetic field, let's just say we had some magnetic flux coming out of the board that's confined to this region, and it's coming out. Classically, if a mu didn't matter and only the magnetic field mattered, if I send something along here and b is 0 here, it's not going to affect anything. If I have it here, it's not going to affect anything. So this and this is going to be the same. But what was experimentally found is that if you go to the top or the bottom, it actually makes a difference. Oh, and it makes a difference in the phase of the wave function, which is a quantum mechanical thing, at least in quantum mechanics.
So I guess it's either you take two measurements and you measure the path to the left and you check like a phase value. You measure the path to the right and you measure a different phase value and you compare them, and they'll be different.
Right.
Where if there was like unperturbed space, it'd be the same. Right.
Well, even if it was perturbed space, if you had that cylinder there, and so it was preventing any electrons from passing through it, but if it had no magnetic field,
Yeah,
then the two would be the same.
right.
But as soon as you put a magnetic field inside the cylinder, the two become different, even though the paths themselves are always outside the cylinder.
Uh-huh.
And even though the magnetic field is not kind of classically acting on the particle going either way.
Exactly, because it's
Right.
confined to inside the cylinder.
Right.
You measure the magnetic field on both paths, so it's both be zero.
Yeah.
So in fact, this is proving that the potential is physical?
Yes, what this really is showing definitively is that A mu does have some additional physical effect that B doesn't have, especially if you want to say this difference is mediated by A mu here. Because A mu can end up giving you E and B, so it has all that information, but it has a little more.
Yeah, and we should point out that when B is zero inside, when B is confined inside the cylinder, A mu is not. A mu is still is non-zero all throughout the space.
What's AMU? The path?
No, A mu is the vector potential that's associated with the electric and magnetic fields.
Yeah, so it's a combination of the scalar potential in the time-like component, and then there's this 3 potential that when you take the cross product of the 3 vector, that gives you the magnetic field. And then there's this phi, and you can have, minus gradient phi minus dA dt gives us the electric field. So A mu is a 4 vector that combines phi in the time component in A and the spatial component and puts it into a 4 vector.
The interference pattern are measured after they combine, right?
So you could bring them back together just to really drive home the point that you want to compare these paths, and the main point is that if you didn't bring them back together, it makes it it closes the loop here and really shows that it's coming from the fact that the flux was enclosed. Because you could also just think about moving a particle in a circle that doesn't surround flux versus putting it in a circle, or you can consider 2 particles going in different paths and joining, and they're related.
The process of going to the left and then measuring a phase and going to the right and measuring a phase and checking the difference of phases is like going all the way around, measuring that phase and checking the beginning phase.
And this is the famous Aronoff-Bohm effect. I've never heard it with those other 2 authors, but it's the same thing.
Yeah, exactly. It's just a technicality.
Okay.
They are the one which discovered it before.
Exactly.
Okay.
Like very often.
And so, I want to point out also, so Maxwell actually said that E, B, and A were all independent, and then Maxwell died, and then everyone decided that A could be thrown away. And then quantum mechanics said E and B can be thrown away, but A is fundamental. Maybe Maxwell was right. I don't know.
And A has the sequence that has the gauge potential, it has the gauge symmetry. The impression that is the one that you can change.
Right, so there's this gauge symmetry associated with A mu where you can do a gauge transformation on this. It'll change A mu, but E and B actually stay the same under this gauge transformation, which is related to why people thought A mu was unphysical. So those are some of the introductory quantum mechanics effects that we briefly mentioned. And if you were to go into a solid state class, you would learn about some of these concepts. We already talked about a little bit of these, and I'm going to go through them again and with further detail. So we have this notion of periodic potentials. So just think of some crystalline solid, and when you have that, there's going to be some atoms with electrons. Some of the electrons are going to be bound, and some of the electrons are going to be on outer shells, which are going to be more free. Now, it gets to a point where oftentimes it's good to just treat the bound electrons as being part of the nuclei almost, and just think of the free electrons as non-interacting. So you get this notion of an electron gas associated with the free electrons. Maybe it's 1 electron, maybe it's a couple electrons per atom, per lattice site. But anyways, you can get this notion of some fraction of electrons going to free electrons, and they're usually going to be less interacting than the bound ones, which makes sense because they're bound because of their interactions. So you find for a lot of simple cases that an electron gas is a good approximation where we just mean these are non-interacting with the lattice itself. And that gets you a lot into the basic material science properties. And another big concept is Pauli's exclusion principle. So what this means is that the electrons, which are spin 1/2 fermions, they cannot enter the same exact state. So if we have two spin states for an electron, and let's just say we have these discrete energy levels, and there's a number of free electrons, we can only put two electrons into one state, because otherwise you would violate the exclusion principle. So,
and the state includes the coordinate in space.
Right. So you can think about it in position, time, space. You can think of an energy and momentum space. So it kind of helps to think of having a quantum mechanical system with discrete energy levels, and then think about the electrons filling up those energy levels. And when you think about it that way, you're going to get this notion that you're going to fill up these energy levels. And if you're at 0 Kelvin, that means there's no fluctuations. So all the electrons are going to fill into the ground state. They're going to go to the lowest possible energy. A temperature would give you some energy to excite to higher levels. But if you remove that temperature, all the electrons will go to the lowest energy levels. And you're going to fill up these levels due to the exclusion principle. And that maximal energy that you get is called the Fermi energy. So you're going to have some number of free electrons. They're trying to fill this energy well, and they're going to stack up and go to the lowest state and fill it up to some Fermi energy. And this is a very good characteristic energy that is useful for describing different types of materials. So a metal is going to have any allowed energy, and there's going to be some Fermi energy, and if you had some thermal excitation, it could just freely cross over. But what actually happens in insulators is we get this notion of a band gap, and depending on where the Fermi energy is, if the Fermi energy happens to lie in some band gap, then you're going to notice some insulating properties. And semiconductors are actually just in between metals and insulators in the sense that there is a gap, but it's very thin, so you sort of get some properties of both. So this is just going into the foundations of the difference between conductors and insulators, really, from the notion of quantum mechanics coming from the Fermi energy driven by Pauli's exclusion principle. And we briefly mentioned last time, I'm going to go through these in more detail on future slides, but we had this notion of block bands and gaps associated with the insulators. And we also had this notion of the discrete energy levels coming from magnetic fields. So there's this notion of continuous bands and gaps, and then this notion, and these bands and gaps are coming from a lattice. And then if you have any system, whether it has a lattice or not, and you apply a magnetic field, you're going to get discrete energy levels. So if you combine a lattice with an external magnetic field, you're going to get this duality of continuous bands and discrete energy. And you can then get this interesting dimensionless quantity because you can have some lattice size, which is going to have some area A. Let's say if you have some 2D lattice, and you can imagine how much magnetic flux goes through that area. And by using Planck's constant, the speed of light, the electric charge, and the magnetic field strength with the area, you can get this dimensionless quantity, which makes it very number theoretic because we're taking out the man-made units and getting to the foundational math. So this dimensionless quantity connects to number theory because we're stripping out the man-made physical units. And
What's the name of that dimensionless quantity?
you can, well, I guess it would be like the ratio. The dimensionless quantity would be the magnetic flux divided by this thing.
Okay. They don't have
Actually, maybe, so, yeah, I mean, you could think of the ratio, or you could think of, like, yeah. I mean, the basic point is that you can, from the units itself, actually, this B this thing is the ratio. This is probably a little sloppy in the sense that phi naught would probably have the flux out. You'd use HC over E and then use B and A to get the magnetic flux, and then combine those two to get a dimensionless ratio. Sorry, I was a little sloppy there. So the basic idea is you can take your magnetic field strength and turn it into a dimensionless quantity. And that's what we've been seeing on the plots for the butterfly. We're plotting the energy versus this phi, which is that dimensionless quantity coming from the ratio. So now we'll actually kind of describe this plot in more detail. I pulled this slide back and just changed a few things. So with these block bands, let's just set the magnetic field to 0. And we have some periodic potential. It turns out that the wave function is going to be periodic up to some waveform that you can have. The point is that this function here ends up being periodic. And A is associated with the vectors found in your lattice. Let's say there's simple roots of a lattice or something like that. And so you can have some integer values going into this n and dotting with that to push you around on the lattice. And this is going to be periodic. So we have some Hamiltonian, which is in terms of p squared over 2m, which we can think of p being, there should be parentheses here, h bar times k, or actually wait, is that h or h bar? Anyways, maybe off by a factor 2. But basically, we get this parabola from the energy being like k squared. So this is a really clever plot because it combines a lot of information in a clever way. So we're thinking of E versus K, and we get this parabola coming from the Hamiltonian. And we want to solve for energy solutions. And we know that the solutions have to be periodic. And basically, we can just plot different solutions with different frequencies. So we're going to have some solution with some energy, but it can fluctuate based on the mode. And essentially, if you can get the boundary conditions to work out so you can fit these modes into the parabola, then that ends up defining what are valid energy bands. And then the gaps end up being what's missing. So by studying this system, you can figure out where the gaps and where the bands are of allowed and disallowed energy in a periodic lattice. OK, and to go into Landau levels, if you apply some external magnetic field, let's just take out, we're not in a lattice now. Let's just think about a magnetic field. What that does is it gives you some canonical momentum, yeah, h bar k. And the canonical momentum includes this electromagnetic potential that Maxwell called an electromagnetic momentum. And what you can do is choose a gauge. So this is a particular gauge that I chose where I'm having a point in the y direction, but it has b times x as its quantity. And when you do that, that ends up giving you this Hamiltonian because you want to use the canonical momentum in the Hamiltonian. And since this includes x, we actually end up getting a harmonic oscillator because we have px squared and we have x squared. Sorry, that shouldn't be a hat. That should be just x. So we get...
So your y hat there, the hat means a unit vector, right?
Yeah.
And then the h hat and the p hat, that hat means operator.
Yeah, OK, yeah. There's a mixing, there's an abuse. Hat is sometimes used for unit vectors, and hat is sometimes used for operators. So here I meant to use it as a unit vector, but here it's now the operator.
You were switching hats.
I was pulling information from different places, but yes, good stuff. Awesome. So we remember that a harmonic oscillator basically is a Hamiltonian that is p squared plus x squared. And so this coefficient out here ends up giving you some resonant frequency associated with that harmonic oscillator. So the magnetic field strength determines some resonant frequency of the system. And you get these energy levels that are indexed by an integer value n, precisely as we find in the harmonic oscillator, because the Hamiltonian ends up being identical to at least the one-dimensional aspect when you consider the x. So we get this 1D harmonic oscillator with discrete energy levels. And if you had an infinite potential well, and you go towards the center, you're going to see these flat energy levels, which are called Landau levels. So does anyone have any questions here?
Yeah, sorry, I just have to try to verbally say these more visual conceptual pictures because the symbolism is harder for me. But so it's sort of like I have a periodic lattice. I, in some sense, break the symmetry of it by placing some magnetic field on it at some direction. And then what I have is this pattern, this interaction of the quantum behavior of what it would be without any magnetic field versus how it is when I put this magnetic field on it from some direction. And then the particles at anything other than 0 Kelvin are always oscillating, at very least due to quantum fluctuations if you bring it down ultimately low, but always with some ambient temperature in those. And so in some sense, we have like Moiré pattern effects in the quantum path potentials, the energetics quantum mechanically, it's sort of they're interacting and interfering, and so then we get these statistical potentials that represent that really manifest as these butterfly patterns and whatnot. Is any of that a conceptual grasp? So like with Moiré patterns, you have these dark and light zones, you have these sort of no-man's zones, and then you have these concentrated zones, and so these Landau levels, are one form of that.
I don't think the Landau levels, I don't think this simple system relates to Moiré patterns. For the butterfly, we experimentally measure the butterfly using a super Moiré pattern because we combine essentially two lattices with a magnetic field and put them at a special angle. Yeah. So the Moiré pattern is coming from the geometric arrangement that we're considering, not necessarily the quantum mechanics.
Yeah.
So
I meant more like a very general Moiré pattern, not the Moiré pattern that is from two periodic systems related, but in some sense how this magnetic field, right, with its discrete quantum energetics is acting upon the lattice potentials, and in some sense you have a relationship between those two separate objects, and that relationship in quantum mechanical terms is all about probability, the interference of constructive and destructive of the probability waves, right, in this system. So it's sort of Moiré pattern in that sense, where there's
yeah, I mean, certainly if you have some lattice and you apply a magnetic field and then you slightly vary the magnetic field, the energetic profile is going to change a little bit, and you could compare those two. I don't know if it would look literally like a Moiré pattern, but there would be some shifts.
Yeah,
and
I should say more just interference.
Yeah.
But that's what Moiré is. It's an interference pattern, but this is a quantum mechanical interference.
But here, if we change the magnetic field, it's not really causing interference because changing the magnetic field is actually doing two different experiments.
Okay.
So we don't really apply two magnetic field strengths at the same time.
Okay.
We would just add those, and that would, whatever its total.
But with everything fluctuating and oscillating, right, then even without changing the magnetic field, you have this constantly changing set of relationships because everything is fluctuating.
Yeah, it depends, I guess, what you could have things fluctuate as well.
I mean, one thing is in quantum mechanics, people often doing quantum field theory, they talk about 0-point fluctuations and say everything's always fluctuating. But that's a little bit too simplistic.
Yeah.
In a lot of quantum mechanics, like with the Landau levels and stuff, you find stable energy states. And the stable energy states have a sort of fixed phase pattern, and then it oscillates in time. The phase oscillates in time, but it's just that the phase is sort of like having a steady progression in time, and it's uniform throughout the whole state.
Okay.
So that the energy state, the energy is not fluctuating. The energy state is a fixed stable state, and the wave function has a fixed stable shape. So that fixed energy
It's
state.
just getting laboratories other than ultra, you know.
But the thing about quantum mechanics is that quantum mechanical systems have these stable stationary states.
Okay.
So an important characteristic to consider in your experiment is what is this value of h bar omega c? That's going to determine the distance between these energy levels, and then you can compare that to k times T, the temperature.
Okay.
So if your temperature is large enough, you're going to have thermal fluctuations that allow you to hop levels. But if the temperature is really cold, then these energy levels are discrete, and I can only fluctuate this much, but I can only have this one energy level. So the energy is going to be very fixed and discrete, as Richard's talking about. So a lot of these experiments are often done at cold temperatures as well.
Okay.
So yeah, so we introduced this idea of the periodic lattice with the block patterns, and then the Landau levels. So when you combine them together, you get this notion of Harper's equation, which includes the lattice with the magnetic field. And basically a way to schematically see this is we know we have this Hamiltonian, and we know the solutions have to be sinusoidal. And I just wanted to point out, if let's just say you wrote something like E naught times sine k times a, and you Taylor expand that, you're going to get essentially momentum translation operators, except you want to use the canonical momentum. And if you think about what this is doing, you could you end up, if you're actually doing it more rigorously, you'll end up getting these small shifts by the lattice distance. Let's say you have some square lattice, and you have some distance a with some magnetic field perpendicular to lattice. So here, the magnetic field is pointing in a direction perpendicular to the lattice itself. So it's even simpler than what you were envisioning in your example. But here we end up seeing that we have psi at 4 different locations that are referenced, x plus a, x minus a. And then when we shift in the y, since I chose this gauge, it turns out that sines are complex exponentials. So I get this exponential factor here, this complex exponential, in terms of these quantities coming from the canonical momentum. And they get added as phase factors when I go to y plus a or y minus a. And these are all related to the energy at psi of x, y. So you can end up getting this equation, Harper's equation, from Schrodinger's equation when you combine these two concepts of the lattice with a magnetic field. And I did go over this before, but yeah, so you can then basically get this notion of a recurrence relation. And this notion of phi is precisely related to the stuff here. So the factor in the complex exponential turns into this, and then this theta is related to phi, which is the magnetic flux quantum that is being plotted on the butterfly. So we get this iterative formula here. And so we can have this recurrence relation in terms of this matrix that brings us to the next step. And if we consider rational values of phi, it turns out that if you have q values, then you only need q operators to bring you to the next state. Basically, you would keep applying this matrix, but you would eventually find that there's only a finite number of them when I have a finite number of bands. So it turns out that through this equation, you see the number, after we've also analyzed the butterfly previously a lot, we know that this q relates to the bands, the number of bands. And then it turns out each band has this associated operator that is part of the recurrence relation, such that if you combine all the operators, it's not like this is a root of unity, but it's sort of similar in the fact, like if this came back to itself, then it would be root of unity, but it gets shifted. But there's a periodicity in how it gets shifted from the band structure. And you can solve for these energies by looking at these matrices and then finding the trace of it and solving for it, which I'll talk about.
So it's like a recursive function because it keeps getting shifted.
Yeah, we have this recurrence relation here because we have n plus 1 and n coming from n and n minus 1. And then that gives us some matrix. And this matrix is in terms of the energy and ky. And you can basically look at the trace of this matrix and then solve for the energy based on what KOI is. So yeah, then you can actually take this ratio of psi n over psi n minus 1, and you get this even simpler recurrence relationship that gets rid of the matrix and is just kind of reviewing some of the previous concepts that we discussed before about Q being the number of bands. But now we see from that matrix equation, and if we look at the trace
here, can you go back to the previous slide? What was Q?
P over Q.
And the Q is just.
So we're looking at values of phi that are rational and putting our magnetic field on this 2D lattice tuned to that strength.
And Q is a rational, or P over Q is a rational number.
Yeah. If we're assuming it's rational, then, so yeah, if it's irrational, then you would never see this periodicity because you would need an infinite number of different operators.
Q is the number of operators you need there.
Yeah. But since it's the number of operators and you combine it together, you can look at this matrix here. Actually, I probably didn't describe this in the best order. Let's see. Yeah, OK, let me just go here. And I probably should have ordered it better. But basically, if you look at the trace of that matrix, which combines the operators associated with Q, then you can plot this trace as a function of energy and find the bands that way. And there's this criterion. So I put the energy on the x-axis and the eigenvalues of m on the y-axis. And if you end up setting that ky to 0, then you can just look for these values. And that way you simplify the problem. And you can find the bands that way. So you get some solution, and then you look for when the trace of m is in between -4 and +4. And you see the energies on the x-axis. And you say, OK, from here to here, I can have this energy. So that's an allowed energy band. And then from here to here and here to here. So for Q equals 1 over 3, we get 3 bands. And Q equals 2 over 5, we get 5 bands. So there's this kind of paradox between the discrete and the continuous, because you can infinitesimally change phi a little bit, and the band structure radically changes, which is hard to intuit because if you just slowly vary something, you would think it wouldn't change the system too much. So it was thought to potentially be paradoxical, but it turns out not to be. And the reason why kind of helps if you consider different examples. So I could look at 1/3, or I could look at 10,000 divided by 30,001. They're really close, right? But this has 3 bands, and this has 30,001 bands. But even when you look at 100 over 301, you can't even see the gaps. So here I have 20 over 61. It's pretty close to 1/3, but not that close. There's almost just 3 bands, right? But if you zoom in, you see there's actually some gaps in there, but they're really small. And as you get closer to 1/3, at rational values, the gaps get smaller and smaller. So at this value, you would be really close, and you wouldn't even be able to see that. We can't even see the gaps here at all, but they're there. So I guess there's like 298 really small gaps somewhere in there, maybe plus or minus 1. So this kind of resolves the paradox when you realize this, because now we see, oh, OK, these rational values with a low q have a low number of bands. But then if we go away from it, there's just going to be these really tiny gaps that appear.
But that's just like the bands themselves, because if you like solve a Schrödinger equation for a potential, say one single square well, you'll get, if it's shallow enough, you'll get just one energy state. But then if you have 2 square wells side by side, you get 2 energy states. And like 10 square wells side by side, you get 10 energy states, and they get closer. So as you go to a lattice where you got billions and billions of these, it's like you have billions and billions of energy states that are all getting so close together, they blend into a solid band. So it sounds like it's the same thing that's happening.
Yeah, that is an interesting way to think about it. Yeah. Yeah, that definitely works as well. Sweet. So now let's look at another example to get into some of this continued fraction stuff and analyze this concept a little deeper. So we could consider something like 3/19, which you can think of as being 1/6 plus 1/3. And what this shows you is you should get this notion of a sixth coming out, but also this notion of a third. So what that might look like? Well, first of all, you can plot this example here, and you're looking for values that are in this strip here. It's hard to see when we have it zoomed out so much. But when you start to zoom in, you can actually see, if I zoom out enough, I see 1, 2, 3, 4, 5, 6, depending on how you count. You do sort of see 6 regions if you zoom out enough. But if you zoom into these with more resolution, you get these notions of triplets. And so it's fractal in that sense, where you see the 1/6 on a large scale, but then you zoom in and you see the 1/3. And this pattern here is very similar to what we previously saw here. It's identical. So the 1/3 pattern kind of gets re-expressed fractally in that sense. And so you can continue this further, right? If I had something like 15/38, I could start to decompose it. And so it has 3 hierarchical levels. The first would be governed by 1/3 at some large scale. Then there would be 1/2 at some medium scale. And then 1/7 at some smallest scale.
That is so cool.
Yeah. So then you really start to see how you dive into irrational numbers by looking at their continued fractions. So yeah,
You're moving
basically,
from one rational number to another rational number. You go by all these an infinitude of
irrational.
irrational harmonics.
Yeah. Yeah, definitely. Yeah, because if you're going to continuously vary phi, you have to go through all these irrationals. A lot of them.
The golden ratio is a continuous. Oh, okay.
So the golden ratio has a very simple continuous fraction. So part of what Hofstadter ended up contributing to this field has to do with different ways of representing continued fractions. So Asbel studied Harper's equation in the 60s and noticed some of these patterns a little bit, but didn't fully grasp it. So he made a claim that simple continued fractions describe these systems associated with Harper's equation. And the butterfly is an example of that. But it turns out that there's this notion of simple, which always has plus signs here, and this notion of nearest integer, which can have plus and minus. The difference is, if you look at what this converges to, it's 1.618, which is closer to 2. So if you go to the simple continued fraction, it's not the nearest integer because I start with a 1, not a 2. But it doesn't always work out that way. So in this case, with the silver ratio, I can represent it this way, but it's closer to 1 than 2. So in this example, the nearest integer continued fraction ends up being the same as the simple. So as this is being discovered, this could be confusing because there's a lot of examples where they are the same, and you just, this is the simple one to consider, so it's probably that. But Hofstadter had used this int function, and he had been interchanging numbers here and here and swapping them and understanding how these continued fraction series are related to the same ratios. And so that experience he had just playing around with the number theory helped him here, because that ended up being the solution. Is there was a slight mistake in assuming the simple continued fractions. He needed to take everything in the literature and switch from the simple to the nearest integer, which is exactly what his interchange function was doing. So that's why it felt so miraculous for him that he was in the right place at the right time. So this nearest integer continued fraction really relates to the butterfly recursion, which happens to be the same for silver but not gold ratio.
For the simple ones, you can't really do that, right? Because it's just, like for example, the golden ratio just has 1. So when you use the nearest integer, then you can have 2.
No, the golden ratio, it works. He's doing it up here. The blue and the red.
Right. But if you just have 1 band, right, which is what David showed before, the number 6 and the number 3 here would be just always number 1. How are you going to show that number 1?
Right. So I guess the point is, from what we previously learned, we understand that these bands, the structure of the bands and the recursive nature of the bands, the fractality of them, relates to the continued fraction expansion. But there's multiple continued fraction expansions you can have. So I could represent an irrational number by different continued fraction expansions. But then that begs the question, which expansion is the physically interesting one that describes the butterfly?
Let me ask something. Maybe somebody knows. I don't know. For rational numbers, I'm guessing maybe for rational numbers, there's just one unique continued fraction expansion, or is there more than one, even for rationals?
I would think that there would be multiple. I mean, because I would think.
You can just start with that.
Yeah. Like I think once again it would depend if it's above or below that 0.5 kind of.
So they're not equivalent when you look at the butterfly, like for different.
Okay, so I guess the point is these two are the same irrational number, right? But if I set phi to be something related to the golden ratio, am I going to see a lot of stuff with 1s, or am I going to see a lot of stuff with 2s?
Right. That's also what I want to know.
Right. So what Hofstadter found is that you need to go to the blue one, this nearest integer.
Okay.
Yeah. So now that we understand this, it's more clear how the irrational and rational fluxes are related through their continued fraction decomposition, because at the end of the day, once you have a crazy rational number, it still has a continued fraction. It'll just terminate at some point. But then an irrational number would just go to infinity. So we see that irrational value, just the self-similarity, would keep going lower and lower levels. And it could change, or it could be the same, like the golden ratio with all its 2s in the nearest integer decomposition. The 2s are all the same, so it's going to be self-similar. But you could still have some other irrational number that's not self-similar, that has values changing erratically, but you could still understand their properties in this way. So these irrational fluxes lead to a Cantor dust of bands, and this is just a quintessential example of a Cantor dust. If you go to this infinite limit, and if we look at the golden mean, and we look at if you basically take rational approximations, which is following the ratio of the Fibonacci sequence and watching it converge phi, if you take all those sequences, those rational approximations of the golden mean, you start to get one level here, one here, and each time we're going down, it's going to the next rational approximation, and we see it's following this Cantor dust-like pattern. So as we go to the irrational number, we're approaching the full dust. And also, we can see it in this sense, but then we can also zoom in So we see a triplet here, but then we could zoom in here, and this is what it's showing here. There's this self-similarity because for phi, the numbers are all the same, so it's going to be the most self-similar. So we have -2 to 2 here, but then we zoom in, so we go from -0.2 to 0.2, and then we zoom in by another factor of 10, and we see the same pattern reemerging self-similarly. And now we mathematically understand that it's because the continued fraction expansion, when I use the nearest integer expansion, these numbers are all the same.
So is it self-similar or is it infinitesimally not self-similar?
I don't know what infinitesimally non-self-similar means.
Exactly self-similar, or just very close approximation to.
Well, it distorts at each level.
It looks like, but it's like it can be a scaling issue.
Yeah, I'm not sure. I mean, it looks exactly to me, but I think for this example, when you consider the irrational value, that's when you would get it to become more self-similar. Like if you do a truncation with some rational approximation, you're going to notice those features. But I don't know, it might get distorted. But then again, maybe not, because
Does every irrational number have a harmonic like this that's infinite and fractal? I guess I just want to look at.
Well, it seems that there should be a difference between the transcendental irrationals and the regular irrationals, the algebraic irrationals. There's a big difference between those two classes of numbers.
Yeah.
What's the factor between one and the other in the x scale? It's not exactly 10, it's close to 10, what it is. Algebraic.
it's close to 10. I don't know exactly what it is. I didn't make this plot. I just pulled it from the book. But they're zooming in by approximately a factor of 10.
She didn't mention that, did she, about the behavior of transcendentals? Because transcendentals don't have a continued fraction or analytical, algebraic expression.
But it wouldn't go dot, dot, dot in some sort of pattern.
So here's the thing. I think any irrational would have some continued fraction approximation. It just would be highly irregular.
It would be infinitely irregular. Like it wouldn't regulate itself. You couldn't
Right.
write it down
So-
on paper and say dot, dot, it repeats this.
So you're saying
Phi is the most self-similar in the sense that the continued fraction expansion has all the same numbers. But any irrational could have A, B, C, D, with all those numbers being different integers. And it could just not repeat ever and just keep going. So when I go, I wouldn't notice the same notion of self-similarity. I would notice this notion of scale. Let's say I had 3, 2, 1, right? And a bunch of other random numbers. Like at the largest scale, I would see that 3 nature coming into play, but I wouldn't see that 3 at the lower scale because I would see the 2. And then I would go in and see whatever is associated. So at the end of the day, what this is suggesting is what really matters is the continued fraction expansion. So then I would just have to think a little bit more about, okay, do all transcendental numbers have some random thing here? I would think so.
It seems like if you had a repeating continued fraction, then you could algebraically manipulate it so that you get an algebraic solution to the irrational number.
Which would mean it's not a transcendental.
Which would mean it's not transcendental. So transcendental means non-repeating, infinite, but non-terminating,
Non-repeating, non-terminating.
Right.
continued fraction.
Or not having an algebraic expression.
Okay,
And
if you can combine transcendentality that way, then yeah, should hold.
I don't know if it's true for sure, but yeah.
I always heard it just defined as a number that does not have an algebraic expression.
Yeah, it's not a solution of a polynomial equation, as usually what I hear, right?
Oh.
Right. Like, okay. So for the rest of the talk, I'm going to go through some of the fundamental physics concepts that go into the topological aspects of condensed matter. And I'm not going to fully connect it to the butterfly, but I want to provide that introductory material and review some aspects of topological insulators and talk about the quantum Hall effect, which is an example of a topological insulator. And then briefly suggest how some of this stuff is related to the butterfly, but then save that for the next talk. So before diving into the quantum Hall effect, there's this notion of the classical Hall effect. So we can imagine having some current which provides some electric scalar potential and gives some electric field. And then we can take a magnetic field that's going to be perpendicular to that electric field. And then we can measure the voltage that is perpendicular to both of those. And to see what's going on here, we understand that through the Lorentz Force Law, actually, all right, so this classical Hall effect, you're going to have this electric potential and this perpendicular magnetic field. And what you're actually going to measure is the voltage, but a voltage in the transverse sense. So usually you would think of measuring a voltage here, from here to here, a voltage drop. But actually, we're going to do it transverse instead. Rather than measuring the voltage drop from here to here, we're going to measure the voltage drop from here to here and look at that. And it'll end up depending on the magnetic field. We'll see a little bit more in a bit for why that is. But basically, we have voltage equals the current times the resistance. And so you get this notion of resistance, resistivity, which is related to the resistance and the properties of the material. So you have some wire. It's going to have some cross-sectional area and some length. That'll give you the resistivity. And the inverse of that is related to this conductance here, sigma. So sigma is 1 over rho. And so the classical Hall effect ends up looking at rho xy and rho xx. And xy is referring to the transverse, because we're applying a current in one direction and measuring a voltage in the other direction. Usually, you apply a current and measure it in the same, which would be the xx. But classically, we see that due to the magnetic field, as we increase the magnetic field, the transverse Hall voltage, or I guess the Hall resistivity, ends up increasing linearly. And the reason for why this occurs is through the Lorentz Force Law. I have some charged particles moving as my current, and I'm applying a magnetic field. So there's going to be some velocity, and I apply a magnetic field. That's going to make it curl. And so that curling is going to push one charge in one direction and the other charge in another direction. And that's why in this picture, as I increase the magnetic field, they're going to curl one way or the other way depending on the sign of their charge. Right? So if the magnetic field is 0, they would just follow the current. But the increasing magnetic field is making it curl away and go transverse more and more. And that's what's creating this Hall voltage, which then leads to the resistivity measures. And then if you take a 2D electron system with a really low temperature and a really strong magnetic field, it turns out that you get this integer quantum Hall effect where there's discrete levels associated with the conductivity for the transverse Hall conductivity. And you can end up studying more complicated interactions and find that when you add in interactions for certain systems, depending on the lattice, depending what the system is, sometimes you're going to get these quasi-particles coming from the interactions. And so if those quasi-particles have fractional charge, then you get an integer quantum Hall effect on the fractional charge, which gives you the fractional quantum Hall effect. So the fractional quantum Hall effect is just the integer quantum Hall effect for these quasi-particles with fractional charge. And you usually get this ratio that is characteristic of that fraction, which is some filling factor. And I just want to briefly mention there's some other effects too. So there's this notion of anomalous Hall effect, where in some cases, if you have ferromagnets with some strong magnetization, they can have this own effect. And it's still not fully understood, but they do observe this. And what these are interesting because you can actually find this effect without an external magnetic field, because the magnetization of it sort of acts as that magnetic field. But it's really more complicated than that because it involves the magnetization and spin orbit coupling interactions. But then there's also this notion of a spin Hall effect and quantum spin Hall effect, which has to do more with a spin current than a current of electric charge. So there's this notion of spintronics where they look at quantum spin and they get this more abstract version of the quantum Hall effect, but with spin instead of electric charge quanta. And so these two examples are cases where you don't need an external magnetic field and still can see these exotic phenomena. Because obviously, if you want to build interesting things, it's inconvenient if you have to apply a really strong magnetic field, because that costs a lot of energy. So it's interesting to find materials that have these types of properties without an external magnetic field. And this is an active area of research. So
for the,
yeah,
maybe we don't want to spend too
I just wanted to mention these exist. I'm not going
I
to.
just want to ask you a quick question if you happen to know. For the anomalous effect, the magnetic field is being replaced, the external magnetic field is being replaced with the own internal magnetic field structure, right? And spin-over coupling.
I want to say yes and no. Yeah, they seem to be making some point that there's some weird thing that's going on here that isn't fully understood, that it's not just the magnetization's contribution to the magnetic field. Sometimes it's even stronger than what they would expect to get from the magnetic field. So yeah, there's something, and maybe that is what has to do with the spin-over coupling, but
then in the spin Hall effect, what is the thing that's substituting for this external magnetic field? Do we have any idea? I mean, I'm sure in the theory there must be some.
I mean, in theory, it's anything, any quanta with spin.
I mean, yeah, the spin replaces the charge, but what replaces the external magnetic field?
Right. So, yeah, I don't know, to be honest. I'm not an expert in this area. So these quantum Hall states are example of topological insulators, and a topological insulator has an insulating bulk with a conducting boundary. And what ends up happening in these systems is transport on the edge of the boundary is topologically protected. And in this quantum Hall effect, there ends up being this two-way edge transport that we can have. And so, as it turns out, there's a lot of different exotic matter states. And it turns out by we can classify these exotic matter by looking at their topological properties, as that ends up being a very universal characteristic of the dynamics. So we have this notion of the band gap. And when the band gap comes closer together, there can be some non-trivial topological connections that are preserved on the boundary. So if we have some normal insulator, there's just a band gap. And so there's notions of Weil and Dirac semimetals, which end up getting these different fermionic states as quasiparticles on the boundary of the system. And the Dirac semimetal is basically when these gaps end up touching. And then there's notions of topological insulators where you can think of there as being some topological connection, even though there is a gap. Or there's this other notions of semimetals where they're overlapping in ways. So I just want to mention these things. So there's integers found that are quantum numbers in the butterfly as well, which I'm not going to go into detail, but I want to just mention this. So basically, each wing has a quantum number associated with it. And those are going to relate to some of the topological quantum numbers associated with this system. And I briefly just want to mention that. So we can think about this butterfly and, OK, why did I just introduce all this quantum Hall effect? How does that relate to the butterfly? And what actually ends up happening is the defects in real materials end up destroying a lot of these properties a lot of times. So then the defects end up being almost more important than the pure case. So this is what can be frustrating in dense matter, is because you want to idealize everything because hopefully that'll approximate the system well. But then it turns out the defects end up being, in some cases, more important than the actual overlying structure. So part of the disconnect between the quantum Hall effect and the butterfly is related to defects. I just want to point that out. But I guess it's clear how we get these notion of topology relating to the quantization of the integer quantum Hall effect. So there is at least this connection of topology still.